So, like we said, this whole section, this whole chapter is about something called inner products. We started off with this thing called the dot product, right? Talked about orthogonality and stuff. But it turns out that just like how vector spaces, vector spaces turn out to be something more general, right? We started off with Euclidean vector spaces, and then we moved to abstract vector spaces, which basically have the same properties as Euclidean vector spaces. Well, we can do the same thing. We have this idea of dot product, but we can make something like the dot product for an abstract vector space. So the dot product is really something more general and more powerful than just this Euclidean dot product. Okay. So section 5.4 is called inner product spaces. Inner product, or maybe, inner product spaces. And norms. Okay, and it's going to turn out that a lot of the things that we did for the dot product, we can get in the abstract vector space case. Okay, so we won't if we have the Pythagorean theorem, we'll be able to do that in the abstract vector space. Cauchy-Schwarz inequality, this sort of thing, will all work in these abstract settings. Okay, so let's just give the definition first. So V, a vector space. V, a vector space, and you have something that I'm going to write like this: V cross V to R. Okay. A binary operation on V. Okay, so the notation may be kind of strange, but what we mean by this is that you have a way of sort of multiplying two things. So you have something in V, and you have another thing in V, and then you have this thing, which is a number. Okay, so you think of this thing as sort of like a function that takes two variables. Okay, it takes something in V and something in V. Just like multiplication, right? Multiplication, right? Multiplication has these two spaces. You fill in the two spaces, and it gives you a number, right? For the same thing here, we're going to put in two vectors here, and it'll give us a number. Okay, so right. So binary operation. In other words, it takes in two vectors and returns a number. Returns a real number. Okay. So you have some sort of multiplication. If it satisfies three things, V against V is greater than or equal to 0 for all V. And is equal to 0 if and only if V is the 0 vector. 2, you take one vector against another, you get the same thing as if you change the order. For all x and y in V. And 3, if alpha x plus beta y against z equals alpha x z plus beta y z for all x, y, z, and alpha beta. If all these things happen, then we say that this binary operation is an inner product on V. Okay, and we call V with this inner product an inner product space. Okay, the way you want to think about this is to think about the dot product, right? If you have if these guys are Euclidean space, well, hold on, people are still copying. I'm not sure if I'm becoming more impatient as I get older, or if you just students are writing more slowly as I get older. Okay, so the way you want to think about this is just think of the dot product on Euclidean space, right? Dot product. Well, the dot product against itself, right? If you have a vector and you take its dot product against itself, that's always going to be greater than equal to 0, right? Because the dot product against itself is the magnitude squared, right? The magnitude of a vector is always bigger than equal to 0, right? And the magnitude is 0 if and only if the vector is the 0 vector. Okay. Dot product doesn't matter what order you do it in, right? Dot product. If you take a linear combination against and dot product against a vector, well, you're going to get you can split up the the addition, and you can pull out the scalars, right? Okay, so this idea of an inner product is just a generalization of the dot product. Okay. Okay. So right. So our first example is let V be Rn, and we let the inner product be just our old dot product. Okay, and then this is an inner product. Okay, sort of obviously, when we basically created the inner product to satisfy the properties of the dot product. Okay. A second example, I'm going to call 1 prime, is the same thing. So you have V is Rn, but now we have a vector in Rn with all of its entries positive. Okay. We throw in this thing W, and we define a new dot product as summation xi, yi, wi, where I equals 1 to n. Okay, so here our old dot product is of course summation xi, yi, right? The old dot product is summation xi, yi, right? Now we're going to do something funny. We're going to multiply the corresponding components, or we're also going to multiply them by an extra number. Okay, so we call this thing a weight. You don't have to know that, but so you weight the entries by certain values. Like maybe you say, okay, I'm gonna, for some reason I multiply maybe maybe W1 is 1, and W2 is a half, or something like that. So if we have something like, suppose we're in R2. We're in R2, and our vector is 1, 1/2. Okay. Then if you took x against y, it would give you x1, y1 times 1 plus x2, y2 times a half. Okay. So you weight these things differently. Right? Over here, everybody's given the same weight, 1. But over here, in this setting, we can weight things differently. It's sort of like, in a dictatorship, right? If we're having a vote and I'm the dictator, all your weights are given the value, are multiplied by 0, right? And mine is multiplied by 1, right? So like the dictator gets the ultimate authority, and everybody else has no authority, right? Or you can make it a little bit more fair. Maybe you guys, each of your votes gets multiplied by a 10 or something, but mine is multiplied by 1. Okay, so this is just you're weighting the dot product in some way. Okay, everybody all right? Everybody all right? Okay, and maybe I'll just leave it as an exercise. Is this really an inner product? Right? Does it matter if you change the order, for example? Does it matter if you change the order? Will you get the same thing? Sure you will, right? If you change the order, you're just going to get, these guys will flip, you're going to get the same number, right? Does it matter, does it have this linearity property? It's easy to see that it'll happen. Anyway, I'll leave it to you as an exercise. Think about it. Okay. Some more examples. Suppose we have two matrices. Suppose we have two matrices. We can define an inner product on the matrices. Okay. What we'll do is just sum over all indices. So I and j go from 1 to m and to m, respectively, and just multiply the corresponding entries and then add them together. Okay, so right, this is just pretending like the matrix is a long vector, right? That's all you're doing. You have your matrix, you have one matrix, and you have another matrix, and we'll create a dot product by saying just multiply the corresponding entries and then add all those products together. It's pretending that this thing is just one long Euclidean vector. Okay, and that would sort of obviously give you an inner product on the space of matrices. Okay. So that's maybe not so interesting. Here's one that actually is interesting. Okay, let your vector space be the continuous functions on AB. Okay, so continuous functions on the closed interval AB. Okay, so your vectors are functions, right? Your vectors are continuous functions. Okay. Now we define an inner product. The inner product of two functions is going to be the integral of the product. Okay, so so for example, if you have the sine function and the polynomial x squared plus 1, then their inner product would just be the integral from a to b of x squared plus 1 times the sine function. Okay, so you just multiply the functions together and you integrate them over the interval. Okay. So first off, let's look at this first one. Is this an inner product? Is this an inner product? Is this an inner product? Well, to be an inner product, you have to satisfy the three properties, right? So the inner product of a function against itself has to be greater than or equal to 0. Is that true? If I take a function, if I take a function and inner product against itself, what do I get? Well, I get the integral of f squared. Right? Is that greater than or equal to 0? Sure, right? Because you're integrating a non-negative function, right? So this is going to be greater than or equal to 0. Okay. The second part actually is a little bit tricky, so I'm going to it's true, but I don't want to prove it because you have to do a little bit of trick. It's a little bit tricky. Okay, so I'm just going to say yes, number 1 is true, even though we haven't done all of it. Number 2, is it true that if I take the inner product of f against g, then I get the inner product of g against f? Sure, right? Because I'm one way I get the integral of f times g, the other way I get the integral of g times f. Right? Those are the same thing. Right? Okay, so that's okay. Number 3, is it true that if I integrate, erase it. Number 3, is it true that if I take the dot product of af plus bg against some function h, I get alpha fh plus beta gh? Think about it for 1 minute and then tell me. Talk to somebody, say, yeah, sure, or no, I don't think so. What's the answer? Yes, yes, absolutely, right? Because if you look at this thing, it's the integral of alpha f plus beta g against h, right? And this thing over here is alpha times f times h plus beta times the integral of g times h. Right? Everything from a to b, right? It's pretty clear that these things are equal, right? Okay, so that's true, right? So yeah, so there's an inner product on the space of on this vector space of continuous functions. Okay. So it's not all things that look like Euclidean space. Okay. Version 3 prime. Let W be in CAB with W of x greater than 0 for all x. Then you can make a weighted inner product in the same way. You take the integral of f times g times w over the interval ab. Okay, so you have your interval ab, you have some function, right? You have some function w, and you take the product of f and g, but you also multiply it by w. So you emphasize certain parts and you de-emphasize certain parts. Okay, this creates an inner. This also turns out to be also is an inner product. Okay, one more example of an inner product. Let V be the polynomials of degree less than n. Okay. And pick any n distinct points in R. Pick n distinct points in R, call them x1, x2, through xn. Okay. So here's R. You choose n distinct points there. Okay. Define for polynomials. Take two polynomials and we define an inner product by doing something funny. Okay. We take the polynomials and evaluate them at the points. Okay. And then we add up all those values. Okay, so suppose you have, there's one polynomial, and you have some other polynomial. You have some other polynomials. So there's one polynomial p and one polynomial q, right? And we're going to make an inner product in a very weird way. We have these n points, and what we do is we take the values of our polynomials at those points and multiply them together, and then just add up all those products. Okay, and I say this is an inner product. This is an inner product. Yeah, read.
Does n have to be greater than 0 for that to be an inner product? Because of that rule that says...
I mean, we're talking about polynomials of degree less than n. So yeah, n, remember? Right?
It's n.
Right, this is polynomials of degree less than n. N is some natural number.
So the n distinct points are...
Yeah, that n and that n.
Okay.
I'm not going to use n to mean two different things.
Okay.
N means that n is that n.
Makes sense.
So like,
I got that.
n is n. N equals n. N is not
Equal
n is,
other n.
Yes. Okay, so like maybe P3, okay, or P2. P3 is the same, right? So P3, we've got polynomials of degree 2 and under, right? And you choose 3 points, 1, 2, 3, and right, you've got polynomials of degree 2 and under, right? So they're paraboloid, right? And we define an inner product on them by saying that we take these values, take the products of the values and add them together. Yeah,
So you can just pick like any points?
Yeah, any points. Okay, and I'm saying that if you choose, you choose n distinct points, then this is going to be an inner product. So let's think about why that is. First off, the easy one. Does it matter if we change the order? No, right? Because it would just change the order here. Doesn't matter, right? Second easy one, linearity, right? Suppose we have alpha p plus beta q against some third polynomial r, right? Is that going to be alpha p r plus beta q r? Yeah, right? Because what you're going to get here, this is going to be summation alpha p xi plus beta q xi multiplied by r xi, right? But you see that that's going to break up into this thing over here, right? Should I write it out? Right? This is alpha summation p xi r xi plus beta q xi r xi, right? But just by distribution, these are the same thing. Okay, so those are the easy ones. 2 and 3. 2 and 3 are okay. Okay. What about 1? Is it true that this is greater than or equal to 0 and that this thing equals 0 if and only if p is the 0 polynomial? I want you to try and think about it for a minute or two. See if you can figure it out. I'll give 2 points on the final to anybody who figures it out. The whole thing. No, 3 points. Yeah, 3 points on the final. Talk with somebody if you want. Talk with somebody if you want.
Yeah, is there something like two
But I was trying to like
it's not going to add up to like pick two shallow negative points and one high positive.
the p-value of any square points is obviously not going to
Okay, somebody have something to say? Oh,
sort of.
Yeah, great.
So for the second one,
the second one, yeah. Well, what about let's do the easy one first. Is it true that this is greater than 0? Or maybe you just want to talk about the second one.
we're going to talk about the first one.
Sure. So what's this? P against P equals summation P xi as I goes from 1 to n. Right? So why is that greater than or equal to 0?
Because it's a square.
Because you've got the sum of a bunch of squares. Right? These are all positive, or at least they're all non-negative, right? Okay, so that's definitely greater than or equal to 0. That's easy. Okay. What about the second one? Is this equal to 0 if and only if p is the 0 polynomial? Well, one part of this is easy, right? If it's a 0 polynomial, p against p is going to be 0. So that's easy. That's easy. What about this way?
So for this, we use the picture,
Yeah.
and we were just thinking, like no matter how many points you analyze P at, it's never going to cancel itself out and equal 0 unless it's the 0 vector. Because you're just adding like points that are greater than 0.
So, no, not quite. Can somebody say, so let's look at the picture. Suppose you know that the sum of the products is always 0.
It's a brilliant idea.
Okay, one brilliant idea coming. Yes, let's hear it.
Well, because if the degree always has to be one more, or the number of points is always one more than the degree of the slopes, you can only have, you're always going to have, even if they overlap and the points where you choose to multiply is every intersecting point, you're always going to have one extra place where they're not overlapping or they're not intersecting. I don't know.
It's P against P. So
Yeah.
there's only there's not enough roots to get
Yeah.
0.
Right. Lizzie, were you going to say that too? Yes. Okay. I'll give it to both of you. Because I could see that Lizzie was like. Okay. So do people get it? Right. Like, look, if the product is if px1 plus pxn equals 0, right? If the dot product equals 0, well, that would mean that all of these things are 0, right? That pxi is 0 for every I, right? That you have to be 0 at each of these points, right? Because there's no way we're going to get, these are all bigger than or equal to 0. The only way we're going to get 0 is if they're all 0, right? If anybody's bigger than 0, that's the end, right? So they all have to be 0, right? So this means that p of xi equals 0 for I equals 1 to n. Right? Okay. But you see what happens. Let's look at the quick case of P3. In that case, we have 3 points where this parabola is 0. 3 points where the parabola is 0. In other words, your polynomial of degree 2 would have 3 roots. Right? That's not going to happen unless your polynomial is the 0 polynomial. Right? Your parabola is going to have 2 roots. At most, it will have at most 2 roots. Right? If it has more than 2 roots, well, it's got to be the 0 polynomial. Okay. So if you since n is bigger than the degree of p, p must be the 0 polynomial. P must be the 0 polynomial. Okay. And so this thing here, this strange thing here, does turn out to be an inner product. Okay. We haven't done too much. We just talked about what an inner product is, if you've been reading. Okay. So we've given several examples of inner products. Okay. So once we have an inner product, we also have all sorts of other things. So, for example, we can talk about what it means to be perpendicular, right? So, let V blah be an inner product space, which I'm always going to abbreviate as IPS. If the inner product of 2 vectors is 0, we say that U and V are orthogonal. We say that these guys are orthogonal. Okay, so for example, suppose we are in the inner product space, continuous functions on -1, 1. The function f of x is 1, and the function g of x is x, are orthogonal. So you can have functions that are perpendicular to each other. Okay? And the reason is that, if we take the inner product, you're going to get the integral from -1 to 1 of 1 times x. Well, that's 0. So it's funny, we can introduce some sort of geometrical thinking to these seemingly non-geometric things. Okay, and that's sort of the point of having the inner product. Definition number 2, if V is in V an inner product space, we define the norm of V as the inner product of V against itself to the 1/2. Okay, so this is a generalization of magnitude. Okay. Yeah, Avery.
Sorry, what is IPS again?
Inner product space. Right? So we can talk about the size of a vector, right? Right? As long as you have an inner product, well, you can talk about magnitude. The magnitude is the square root of the inner product of the vector against itself, just like in Euclidean space, right? So you can talk about how big this function is. Okay. Another thing that we can introduce is the idea of projection. So suppose that U and V are in the inner product space again. We define the vector projection. The vector projection of U onto V as the inner product of U against V over the inner product of V against V times the vector V. Right, which is the same thing as the inner product over the magnitude of V times V over the magnitude of V, if you like to think about it that way. Okay, so we just take the Euclidean definitions and then we, use them in the general space. Okay, and we define. Sorry. Let me just write it down here. We call this thing the scalar projection. So this number here, just like in Euclidean space, we call the scalar projection. Okay. So we're just taking our ideas from Euclidean space and we're extending them to inner product spaces. Okay. Another thing that we get is the Pythagorean Theorem. So suppose V is an inner product space. and you've got two vectors u and v in V. Then if u is perpendicular to V, then the magnitude of u squared, the magnitude squared of u plus v equals the magnitude of u squared plus the magnitude of v squared. Right, so we'll have a Pythagorean theorem for the world of continuous functions. Right, as long as you have an inner product, you can talk about a Pythagorean theorem. Okay. The proof of this is actually really simple. The norm squared is u plus v inner product u plus v. U plus v inner product u plus v. But we have linearity, right? So we can say this is the same thing as u against u plus v plus v against u plus v. Right? Right. We also have commutativity, so we can switch the order. This is u plus v against u plus v against v. And so this is property 3 of inner products. This is property 2, using property 2 of inner products. Can anyone see to the end what's going to happen? See it?
You can
distribute again, so you get u,
and u on v.
V, u.
And then the same thing.
U, v, 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 and then?
And then since they're orthogonal, u on v is 0 and then v on u is 0, so then it's just...
Exactly. Okay. Right? Right. You distribute again, use the fact that these guys are orthogonal, and u against u is the magnitude of u squared, v against v is the magnitude of v squared. That's it. So you see the proof is actually really easy. Okay, everybody okay? Okay. Actually, I think I'm going to stop there because the next thing we're going to do is the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. So remember what that says. That says that if you look at the inner product, the size of the inner product, it's controlled by the product of the magnitudes. Right? Okay, but the proof of that is going to take more than 3 minutes, and also I have the exams to return. So let's stop here for now, and then we'll get to this next time.